Geographers, welcome back. This module will be dealing with atmospheric circulation, wind patterns, both globally and locally, and then also the property of waters. What we're doing is we're building the pieces towards weather. So we already got one of the components with temperature last time, and now we're going to get the movement of the air and kind of bring in the effect of that north-south shifting of the solar energy. So we're putting our pieces together for weather and for climate. So with atmospheric circulation, we'll start with wind, and wind is a function of differences in air pressure. Now, normally when we talk about air pressure, we would measure it at like 15 pounds per square inch. We're not going to use that measurement system. That's for like bicycle tires. When we're dealing with atmospheric measurements, we'll measure it differently. But the more air molecules you have, the more they're colliding with each other, the denser the air molecules, the higher the air pressure. And in general, the closer you are to the Earth's surface, the more air molecules there are. You have higher air pressure at the surface, and then obviously as you get into higher levels of the atmosphere, there's less air molecules as you move up. And we measure, for climate and weather related purposes, we measure air pressure in either inches or millibars. The English system is inches. The metric system uses millibars. Now this is one that it isn't consistent. You're going to see some measures in inches and others in millibars. I tend to use millibars more than inches, but I know that there's going to be a few charts that show up that measure air pressure in millibars. It's the same general concept. It's just the amount of air pressure pushing down on a general location. So the greater the air pressure, the higher the more air molecules there are. Now, the chart on the lower left shows some record lows. Some of those have been recently changed, but I didn't find a nice upgraded graphic for it. But you'll notice that all the low pressure ones are associated with storms. And so the greater the pressure, the lower the pressure is, the stronger the storms can be. And the opposite for high pressure isn't associated with storms. You'll notice those are Alaska, Yukon Territory, Siberia for the high pressure. So those are associated with cold air. And cold air sinks. And so those areas where they're sinking air because it's cold, it's bringing with it more air molecules. So you're adding, as air sinks, it can't sink into the earth. So if it's sinking through the atmosphere to the Earth's surface, it concentrates at the Earth's surface, creating a higher pressure. There are other ways that this happens as well. It's not just through storms or just through cold temperatures, and we'll talk about those in a little bit. Also, what's normal air pressure? That's a tough call. The average is around 30 inches or about 1,013 millibars. But if you're above it, it doesn't make it high pressure. If you're below it, it doesn't make it low pressure. There's something else that affects that. So if we look at measuring air pressure at the surface of the Earth, and just as isotherms were used to measure temperature, isobars are used to measure barometric pressure, which is what we're seeing here. And this area has over 1,020 millibars of air pressure. This has below 996 millibars of air pressure. And for any location, whether you're high pressure or low pressure, depends on what's near you. So if you're in this part of Idaho, in all directions, the air pressure decreases. So you're in an area of high pressure. If you're in this part of the southeast, in all directions, air pressure increases. So you're in an area of low pressure. So it wasn't the number that made it low. It's what's around you makes it a high or a low. Take this, for example. If we look at this area through here, in all directions, it's an area of increasing air pressure. So this is a band, it's called a trough. It's a trough of low pressure. And over here, but it's the same number. It's about 1,008. This is about 1,008, but if you go away from it, air pressure decreases. So this is an area of high pressure through here. So it's not the number, it's just what's next to it makes it an area of high pressure or low pressure. And why that's important is that air moves from the high to the low. And the area that has a concentration, a great deal of air molecules, is going to feel their air molecules drawn towards where there's less air molecules. So the low pressure is pulling the air molecules towards it to replace the missing air molecules here. So the greater the difference, though, between how high is this high and how low is this low is going to determine the wind speed. So if we look here over this distance, we have a gradual pressure change. We go from 1,028 millibars to 1,020 millibars. So we've got a pressure gradient, and so the air moves from the high to the low, but it's not much of a slope. So here, in a very short distance, we drop 16 millibars. So that very steep pressure gradient means that the air moves very, very quickly. I always like to think of the pressure gradient, the difference in pressure between the high and the low, like a physical slope. So this would be a gentle slope. So if you rolled a marble down it, it would move very fast. This would be a very steep slope, so the marble would move really fast. And that analogy works for lots of things as it relates to air pressure. Because we'll see in a little bit, areas that don't have a slope, the air isn't moving at all. So the gradient, the pressure gradient, is measured with its pressure gradient force. And so the higher the difference in air pressure, the higher the pressure gradient force, the higher the winds. So take a wild stab at what it's like in the middle of a hurricane. That extremely low air pressure in the middle of a hurricane creates a really high pressure gradient force. So what are the winds in a hurricane like? They're very, very high. Same thing with a tornado. Really high pressure gradient force, you get really high winds associated with it. So the analogy of a slope, if we look at measuring it in air pressure at over 30 inches, I told you it was going to go back and forth, and then it decreases as you move away. So the pressure gradient's low over here. It's very similar to if you're looking at topographic maps, and here's a ridge, and here's a slope that goes down, and then there's the valley bottom, and then there's another slope over here. So the air will move from the high to the low, from the high to the low. Now, this is because there's a pressure gradient. There's a pressure difference between here and here. What if you were here? Is the air moving here? There's no pressure gradient. So if this was the bottom of the valley and the marble was here, it's not going anywhere. It's not going to move up the hills, and so there would be no wind here. And if you were perfectly placed in the middle of the pressure center, there'd be no wind here. It's almost like you're balanced, being equally drawn in all directions. If you had a marble here, you were equally drawn in all directions. So the slope, if this was a cliff, how fast would that marble be moving? How fast would that marble be moving if you had a really steep pressure gradient? So again, the air moves from the high to the low, and we'll get some of the triggers, what creates the low, in just a second. But in just a modeling situation, it makes it look like, well, air just goes out from the high to the low, but we have to factor in one additional force. The Earth is actually rotating, and it affects the movement of the air. So that deflection of the air is from the Coriolis force. You've all heard of the Coriolis force. And what happens is, I'll come back to this slide, don't worry, that when an object is moving, the rotation of the Earth causes an apparent deflection. So what's happening is that that object started off moving in that direction, and so that was, hopefully the GIF reset's really cute. It's still heading in that straight line that it initially started on, but since the Earth kind of rotated away from that initial straight line it was headed towards, it ends up carving a curved path on the surface. Same thing in the southern hemisphere, that it may have started off in that direction, but the Earth rotated away from it, creating what looks like an apparent deflection. And so in the northern hemisphere, all objects moving through the air are deflected to the right. This affects artillery, it affects golf balls, it affects ocean currents. It doesn't affect your sink or your toilet. There's other things that affect that more dramatically, but in the northern hemisphere, you've got a deflection to the right. And so our air movement in the northern hemisphere is deflected to the right, and our air movement in the southern hemisphere is deflected to the left. So when the air moves out of the high, it's got that right deflection to it as it's being drawn towards the low. And then the low has the deflection to it, which creates a spiral. So the surface winds end up actually, instead of going straight from the high, which is the blue lines, does the black lines. So you get a clockwise, this is northern hemisphere. In the northern hemisphere, you get a clockwise spiral out of a high and a counterclockwise spiral into a low. Our weather systems that move across the United States are a function of these low pressure systems. They're called mid-latitude cyclones, and they have that cyclonic counterclockwise motion with them. Same thing with hurricanes. They have in the northern hemisphere the same rotation, and that'll affect where the damage is done from the hurricane. So it's referred to as cyclonic flow, and so those low pressure systems that are created, they have a counterclockwise, that's a cyclone, and then a high pressure system creates what's called an anticyclone. Now, cyclone sounds really dramatic because it sounds like it's something that's going to destroy some island in the South Pacific, but that's a different kind of cyclone. We're dealing with, these are just normal, what are called mid-latitude cyclones. And the ones that are very devastating are called tropical cyclones. Only weather people would be referring to these low pressures as cyclones and knowing the difference between the two. So when we're talking about this, and as you're reading about it in your textbook and you see cyclone, it's referring to that spiraling motion. If it's a tropical cyclone, those are the ones that are devastating. I mean, we have cyclones moving across the United States right now. And we also have we have a mid-latitude cyclone moving across the upper states, and then we have a tropical cyclone headed towards Florida. Now, this map is showing surface winds, and the darker the color, the faster the lines are moving. Obviously, the heavier, the higher the winds are. So there's an area of low pressure right over the Great Lakes and through here. You can see the air gently spiraling into this. This is a mid-latitude cyclone over here. There's another one kind of forming up here, but it hasn't quite fully formed yet. Those are the cyclonic motion. Here, this is a tropical cyclone headed for Florida. So the tropical cyclone is referred to in our part of the world as a hurricane. So there's a hurricane headed for Florida on August 2nd, 2020. There's some high pressure in through here, but not very dramatic. That's it. There's not a big pressure gradient in this area, so there's not a lot of wind in this area. And then this is the remnants of a low pressure system that picked up a little bit of speed over the Atlantic. So this is a low pressure system, a mid-latitude cyclone headed for the western United States. And you can see that counterclockwise spiraling on it. Oops, ignore that slide. So here kind of a speeded up version of what you were showing before with this has a whole bunch of mid-latitude cyclones forming in this area. None of these are hurricanes or tropical cyclones. These are all mid-latitude cyclones. Notice the time of year. That's not hurricane season in April. This is a hurricane from 2004. Tropical cyclone moving through Florida. You can see the cyclonic motion here, except it's moving significantly faster. You've got the higher winds means the spiral is moving faster. In the southern hemisphere, everything's reversed. And so a tropical cyclone, instead of it spinning counterclockwise, spins clockwise. So here you can see the clockwise spiraling. So if you're in Florida, you're getting onshore winds and waves striking you here, which is causing much more devastation than if you lived in this part of Florida that's getting offshore winds blowing the water away from the coast. Big differences in damage depending on which side of the cyclone, the tropical cyclone, is striking you. And same thing here, where this area is going to get much more devastation than the other. Here we just happened to have a few years ago a whole bunch of tropical cyclones all at once. And you can see the spiraling in all of them as well. So when I come back, we'll talk about global wind patterns. Make sure you've got a pen and paper or pencil and paper ready because we're going to be drawing some things as we get to this particular one. So we'll see you in a bit for global patterns, global wind patterns.